All right, everybody, and welcome once again to the wonderful world of statistics. And today we are talking about the fundamental theorem of statistics. We're still in chapter 18, still talking about sampling distribution models, and we're still really focusing on proportions. We're going to come back and talk about means a little bit later on. But one thing that you'll notice as you move higher and higher into math is that, well, almost every branch has its own fundamental theorem. There's a fundamental theorem of algebra, fundamental theorem of calculus, all sorts of different stuff. The fundamental theorem of statistics is what we're going to be looking at today. It is basically this main theorem, this main idea, upon which all of statistics is centered. Now, we talked last time about a little bit about sampling distributions themselves. We said the sampling distribution of any mean, we were focusing on the average of the proportions, becomes more nearly normal as the sample size grows. Okay, we said we like to have a really big sample, but not too big, nothing more than 10%, but so that our success and failure condition is met, so that we have at least 10 successes and 10 failures. Now, in order to follow any of this, we need to make sure that our observations are independent and collected with randomization. We do not care about what the true shape of the population distribution is. Not the population. We don't care, and I'm going to show you in a little bit why that's so. The fundamental theorem of statistics is also called the central limit theorem. And those of you who have taken calculus know a little bit about limits as being what we approach as either we get to specific values or as we go closer and closer and closer to infinity. Well, the central limit theorem of statistics is a little interesting. It tells us that not only does the histogram of the sample, and we talk about the sample means, but it's really the any average of either means or proportions, it gets closer and closer to the normal model as the sample size grows, but this is true no matter what the shape of the original would be. And I know right now that kind of is confusing. What the heck is this crazy lady talking about? And I'm going to illustrate this. This is one of those things that make more sense with a picture than it does with words. But the big thing that you need to understand is that the central limit theorem works better and faster the closer your original population model is to being normal. And it works a heck of a lot quicker for large samples. All right, now what is the central limit theorem? It says the mean, the average of a random sample, keyword random, is a random variable, a variable that changes, whose sampling distribution can be approximated by a normal model. The larger the sample, the better your approximation will be. Whoa, right? Lots of crazy words. Okay, one more time. The mean of a random sample, the average of a random sample that you took from a population, is in itself a random variable whose sampling distribution, whose shape, can be approximated by a normal model, unimodal and symmetric. The larger the sample, the better your approximation. Now here are those crazy assumptions and conditions again. They're pretty much the same. Independence, the samples must be independent of each other. Taking of one sample should not affect the other. And the sample itself must be large enough so we have not too big, but big enough. These are what our assumptions state. In order to meet those assumptions, we have our conditions. Okay? So we can't go into this directly. What that means is I cannot measure in every sample and every population whether or not one thing has anything to do with another, nor can I look at it and say directly whether or not it's big enough just by looking at numbers that I'm given. You have to check it. So you have to make sure it says someplace in your description that your data, your values were collected randomly. Huge thing. The 10% condition helps us satisfy our independent assumption because it's saying that my sample is not too big where I kind of like put some danger into my independence assumption. But it's big enough to meet my sample size assumption. The central limit theorem does not tell us a specific number. There's no magic place where I say, okay, a sample of size 20, that's perfect. But remember, we have that success and failure condition. That helps us get there, because that's where we have to think about it in context of what you know of the population. All right, now which normal is which? Because again, at the end of the last lesson, I said we have two normals. We have the normal distribution of the population and the normal distribution of the sampling. The central limit says the sampling distribution of any mean or any proportion is approximately normal. Approximately. Not perfect, but gets really close. For proportions, the sampling distribution is centered at the population proportion. So that's what we're talking about our P. Okay? And technically, when we're talking about a population, population is P hat. For means, it's centered at the population means, which is our mu. Now, we're going to be, again, focusing mainly here on P for this unit. But what about the standard deviation? Now, this is important to know. For any normal model, the sampling distribution of the mean has a standard deviation equal to the standard deviation of the population divided by the square root of the sample size. Okay? Now, we talked last class about the fact that the standard deviation of any population when we're talking proportions is root PQ. So again, the standard deviation for any sample with a true proportion of P is the square root of P times Q over N. Success, failure over sample size, square root of all of it. So when we talk about that variation, we're looking at here is the standard deviation declines with the square root of the sample size. We're going to be doing a lot of practice with this in class, but please make sure that you understand that. It changes not directly with the sample size, but with the square root, because your denominator contains the square root of n. So the variability decreases as the sample size increases. We'd like to have a larger sample, but that square root limits how much the sample can tell us about the population. Okay? Now this is the law of diminishing returns, if you've ever heard about that before. If not, don't worry too much. This is what I want you to worry about. We have two distributions again. Okay? This should be a little bit repetitive here. What we're talking about is that the real world, again, the distribution of the real world, the sample, which we might display with the histogram. The second is the math world, the sampling distribution. Okay, so the real world can be all sorts of different shapes and sizes, but the math world, my sampling distribution, follows the normal model. When we're talking proportions, we still center it at the population proportion at P hat or P. And the standard deviation is root PQ over N. Don't confuse the two. And when we're talking about sampling distribution, make sure you use the word sampling. So statistics is a random quantity. That means that you cannot predict it. And it's a random quantity because my samples themselves are random. How am I supposed to know what the average of a sample is if the sample itself changes? Hence a random quantity. But the good news is, for means and proportions, the central limit theorem itself tells us it's okay for us to model the sampling distribution with a normal model. And that's because we have two basic truths about sampling distributions. First off, they come across because your samples themselves vary. And every random sample will be slightly different. You don't normally expect to see the same groups in every sample. So every statistic will be slightly different. And although we can simulate a sampling distribution, center limit theorem makes it so that we don't have to do it so much, especially when it comes to means and proportions, when those are my measurement of interest. All right, so here we go. The process going into the sampling distribution model. I'm going to show it to you once and how the textbook explains it, and then I'll walk you through a couple of examples, some simulations. So what this is, let's say this is my population. Okay? Think about it. Not every population is normally distributed. This one is skewed, and if you remember, my tail is on the right-hand side, it's skewed right. Maybe that means I have a limit to how small something can be, but it can go bigger and bigger and bigger. Now, if I take that that original population, it has a mean of mu and a standard deviation of sigma, and I can take samples from it. Here's my first sample. My first sample, and you probably expect your samples to follow the same distribution of the population model. So here's sample 1, here's sample 2, here's sample 3. But what I'm going to do is I'm going to go into each of those samples and I'm going to calculate the mean. The mean is y bar. That's the mean of this sample. And lowercase s is the standard deviation of this sample. Y bar, mean, standard deviation, mean, standard deviation. And if I put together a graph of all of the means from each of my samples, well, that graph should start to look approximately normal the more samples I do. And not just any type of normal, it's normal that should be centered at the mean of the true population, wherever that average originally came from. So in this one, it's probably over here someplace, because it's skewed right. It's going to pull the mean right of the median. And the standard deviation is the standard deviation of your original population divided by the square root of the sample size. Now let's take a look at what this actually is in action. I'm really excited I get to show this to you because it's actually blocked from school, because you know, a good educational website should be blocked by school technology? Okay, whatever. No, it doesn't make sense. But you can see here I have a population. And there is a way to where you can, it's just like doing a simulation where we say, okay, the probability of falling anywhere in here, and we match it up to the true distribution. Now what I'm going to do is I'm going to tell my computer to randomly grab 5 pieces from within my parent population according to its probability distribution. So let's see here. So right there, that was 1, 2, 3, 4, 5 to make up my first sample. I generated 5 values with this probability distribution. The mean of that value is right here. Now let's do it again. 1, 2, 3, 4, 5. 5 other values selected with the probability as described up here, and the mean fell here. 5 more values, and you can see where the mean lies here. Now let me do 5 of these. 5 more of those. And you can see the more samples that I take, 5 more samples. The more samples I take, 5 more samples. It starts to look a little bit more normal. And what these color differentiations down here mean is the blue is the mean of this population, and the red is the, wait, let's see here. It's supposed to be the standard deviation, so it's just showing you the width of the standard deviation. Let's do another 5. You can start to see it, again, get more and more normal. Now, to do this for a while will take a long time, so let's jump up and let's do 10,000 of those. And immediately, you start to see the distribution approaching more normal. And it's normal because if you look here, my mean and my median are approximately the same. I'll do another 10,000, another 10,000. Hey, let's do 100,000. Let's do 100,000 a couple times. Boom, 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 boom. I'm doing a lot of samples. It's taking me so long. It's awesome. All right, so what happens here is we can see that the more I do, it's kind of hard to tell, but your standard deviation right here It's kind of staying put. It actually gets a little bit smaller. It's hard to tell. But your mean, look at this. Here's my mean of my sample. Here's my mean of the true population. Now, that would kind of make sense because that's a normal distribution. But let's do something wonky. There's a bimodal distribution. And it is slightly skewed. It is slightly skewed to the right because my mean is bigger than my median. Now, if I were to take a sample, whoops, let me do this. If I were to take one sample, you can see the distribution is also a little bit bimodal, and the mean of that one sample is right there. Here's another sample. 5 data sets. There's the mean for that. There's another mean. Mean of yet another sample. Okay, let's do 5 samples at a time. 5 more, 5 more, 5 more. So you're starting to see that we're approaching more of a normal model. This is the distribution of the means of stuff pulled from something with this kind of a probability distribution. If I jump up and I start doing a lot more, it's going to take a little bit longer for us to get to a really pretty normal mode because that's bimodal. But you can see here, the more that I do, and if I jump up to even bigger numbers, it's going to start looking more and more normal. But it takes me a lot longer. So if you can see with the normal model, this is how it maps across here. It's getting there, but it's definitely not moving quite as quick. So let's do one where it is more like what we saw in the practice in the example. So if I just do, oops, let's try to make this a little bit different. Okay, I'm doing a skewed data. Take a sample, mean, sample, mean, sample, mean. Okay, 5 of those in a batch, 5 more in a batch. So we can start seeing it grow closer and closer to that normal model. You see how my normal model itself is changing? That's because my sample size is changing. Now let's jump that up pretty quick. 10,000 samples. Another 10,000 samples. So this is saying I've done this 20,058 times. But you see how quickly that jumped to approximate the normal model, whereas the other one took a lot longer. The closer we are to normal, basically the central limit theorem says, the more my sampling distribution will appear normal. So again, no matter what the distribution of the population is, that distribution will have a mean and a standard deviation. Of all of the samples that you could possibly take with all of their means and standard deviations, if you put those together, the mean of all of those means should approximate the mean of the population, and the standard deviation of all of those means is the standard deviation of the original divided by the square root of the sample size. So there's a lot that can go wrong here. You have to make sure that you know what you're talking about. In statistics, that's what it's all about. Do I even know what I'm dealing with here? You can't make it up. You have to know, are you talking about an entire population? In which case you could use mu or p hat and just straight up sigma. But if it is a sample, and we're looking at either values or frequencies, not true proportions or means. The proportion could be taken from several samples, or is it a mean taken from several samples? Those are going to be slightly different situations. We'll handle each of them separately. And when you're looking at the shape, center, and spread, an entire population, again, you will use mu and sigma. The shape can be anything. I mean, we like it when it's normal, but it technically could be anything. Whereas for a sample, it should look a little, one sample should look a little bit like the entire population. And for one sample, we'll say the standard deviation and the mean are both mu and sigma. That's just one sample. But if we're talking about several samples and we're using a proportion, we're going to center the proportion at mu, at my true population, And my standard deviation is the square root of PQ over N, success times failure over sample size. And if it is a mean, well, very similar. It's going to be centered at the population mean. And the standard deviation of your sample will be the standard deviation of your population divided by the square root of your sample size. Whew, lots of stuff here. And if you're dealing with several samples, remember, shape only approximates normal when you have done enough samples. Too few, and you look like the original. Not as big of a problem if your original is normally distributed, but the more skewed, the more random looking the graph is, the more samples you need, because all of this depends upon independence. Because we can't have too big of a sample size, otherwise it affects independence. And also, well, with statistics, chance is what we're looking for. We're not looking for one thing affecting another. So, sample proportions and means vary from sample to sample. That's the whole idea of sampling variability. And that's sampling error. It's not a terrible thing. Don't think that, oh my gosh, I made an error, I made a sign mistake. Sampling variability itself accounts for a lot of this. You put enough monkeys in a big enough room, and eventually, by sampling variability, one of them will create the complete works of Shakespeare. That's sampling variability. It's unavoidable, but it is predictable, the fact that your samples will vary from case to case. We can describe the behavior of a sample proportion when your sample is random. Number one key thing, it's got to be random, and large enough to have at least 10 successes or failures, but don't forget, not too large, not more than 10%. And we can describe the behavior of the sample means when our sample is random by talking about that normal model, roughly unimodal and symmetric, even when the original population is not. Okay, so there's a lot going on here. We've basically said that it does not matter the distribution of the population. One sample will mimic that population distribution, but the more samples you do, the closer and closer you will get by the central limit theorem to a normal model. A model who is centered at the population's true mean, whether that's the average proportion or the mean of the population, and the standard deviation of your sampling distribution is the original standard deviation divided by the square root of the sample size. All right, ladies and gents, hope you're ready for tomorrow or ready for class whenever I see you, and we'll get started. All right, have a great one.